All right, let's go and get started. Let me get the sign-in sheet passed around. All right, so a couple things. Number one, you all have a present for me today. Your homework 3 is due today. So if you haven't already turned that in, go ahead and do so. Thank you for the shades. I appreciate that. Okay, so homework 3 is due today. Just so everybody's clear on the timeline, we have our first celebration on Friday. We are starting at 8:30, okay? So be here on time. Another issue on bookkeeping, on Wednesday, I am going to have exam 1 review. So I'm going to come in with review slides and what have you. We'll go through the topics that are going to be covered on the exam, and then I'll give you time to ask whatever questions you want, okay? So sound good? Now, speaking of the homework, I know the homework's due today, but I had some questions from some of you, but I'm curious if the email I sent helped, if anybody had any issues or problems. I did want to review something real quick now that you've already turned it in to maybe clarify some things, and I'll use number 3 as an example. So a lot of people were, and I heard this quite a bit from a number of people, that problem 3, they were getting like a really low efficiency, and they didn't understand like how the design was economical. Well, let me explain something, all right? So here's the solution. I'm going to go ahead and show you this now because I want this sort of, gnawing away at the back of your head when we have review. So here's the member that you're designing. You factor the loads, go through and look at your connection parameters, and then calculate a minimum gross area. And your minimum gross area comes out to be about 10.864 square inches, okay? Now, a couple points to make off of that. Number one, this equation was built based off of assumptions, okay? So it could be wrong, okay? That's point 1. And point 2, okay? And this relates to problem 2 more than it does to this one. You can violate this expression and still get a member that works. You will not find this equation in the manual at all, okay? Because, again, it was built based off of guesses, okay? It's just a starting point equation, and that's it, okay? So we calculate a minimum gross area of 10.864 square inches, and then that leads us to pick a C15 by 40, okay? Now, you take that C15 by 40, and you go through and you do the full-blown analysis, okay? You've got your section properties, your gross area, your web thickness, your connection eccentricity, calculate your net area, your shear lag factors, yielding, fracture, and block shear, okay? Now, here's what I want to focus on right here, okay? When you calculate your efficiency, you take PU and you divide it by PPN, okay? PU is your factored load, the 352 kips. PPN is not always this number, okay? It was this number, it just happened to be that number in our example because this value was smaller than this one, okay? You have 3 capacities that you're checking, yielding, fracture, and block shear. That's the lowest, okay? So your efficiency is PU over that, which comes out to be about 92%, okay? So that is the most economical selection, okay? Does that make sense? I know a few of you had questions about that, and I was a little sort of silent because I wanted to see what everybody came up with. But did that clear some stuff up for everybody? Anybody have any questions? Now, one other point I will mention, and I'm going to give you a copy of this on Wednesday, but on problem 2, okay, this is going back to what I mentioned earlier. So here's problem 2. You have the WT section that you're designing. You go through and you do your design expression, and you get an AG min of 7.11 square inches. Does that sound familiar? Again, built based on assumptions, okay? We made guesses to develop that equation. So I'm guessing that my gross area needs to be about 7.11. My trial design is a WT7 by 26.5. If I go through and analyze it, I find that it works. Okay, but its efficiency is a little low. Okay, the efficiency is 89%. Now, like I said, the rule of thumb is if it's 90% or greater, don't worry about it. So this is 89. Should you check the next one? I don't know. It doesn't take a lot of work to go through and analyze the next member down. So let's go ahead and check the next member down. The next member down is a WT 7 by 24. Now let's be clear. The gross area of a WT 7 by 24 is not 7.11 square inches. It's 7.07. It's lower than that AG min. But again, AG min was calculated based on a guess. Okay? It just helped us get towards the right answer. And if you calculate the WT 7 by 24, you're going to find it works. And it's very efficient. Okay? That's iteration. That's the iterative nature of design. On problem 2, I wanted you to have to iterate. On problem 3, I wanted you to have to also consider block shear. That was really the big difference between problem 2 and problem 3. Okay? Does anybody have any questions on these? I know I'm sort of going through the solution as you turned it in, but I know that stuff was going to be gnawing at the back of your head as you have a celebration on Friday. Let me see. Let me see what's going on. Okay, so here's the block shear failure path. So we're considering the path that rips right through this connection in the web. You're not going to consider ripping through here or ripping through there because you're ripping through all that flange that's sticking out. Okay? Now, for your gross area in tension, it is 5 times the web thickness. 5 times that thickness. For shear, you have this distance times the web thickness, but you've got 2 of them. Okay? Now, for tension, the net area that I subtract area loss due to bolt holes, I have half a bolt hole here and half a bolt hole here, so I subtract 1 bolt hole. For shear, I have 1, 2, 3, 4 and a half, and then 1, 2, 3, 4 and a half. So I'm ultimately subtracting 9 bolt holes. Okay? Does that make sense? Is everybody else okay with that? I really want this to make sense as you prepare for your celebration on Friday. Any questions? Okay. All right, so today what we're going to do is we're going to get into design considerations associated with bolted connections, and we're probably going to stop it there because I'll be honest, the actual design and layout of a bolted connection is pretty simple. So I want to go through that today, go through a pretty quick design example and some discussion associated with that. And then honestly, we're probably going to call it because I might talk a little bit about slip critical connections, but I really don't want to get into some heavy detail associated with slip critical because you all have a celebration coming up. So this is a lecture that I think everybody can follow along with pretty easily and keep in the back of your head after the exam. Because I know right now some of you are thinking, well, bolted connections aren't on the exam, so I don't really give a damn what he's talking about right now. Well, this is pretty simple stuff, so I think it'll be easy to follow. All right, sound good? Okay. So let's just sort of pick it up right back here. So last time we did this bearing type connection, and it was a splice connection, if you will. So all the bolts were in double shear. We had A36 plate that was different thicknesses and had different dimensions. We had a different edge distance for the cover plates than you did the center plate. So technically you need to go through and do bolt bearing twice. Now let me pull up the calculations real quick. Let me see. Pull up the calculations real quick. So let me, oh, come on. There we go. All right. So here's the member. I'm actually going to erase this little drawing right here because this was me answering a question, and I want to leave that off. So here's the example. We had 1-inch diameter bolts. Our hole diameter was 1 1/16. We had A36 steel, so there's our ultimate tensile stress. For bolt shear, we just said, all right, we have 80.1 kips per bolt, and we looked that up based on table 7.1. And then we said, well, if that's the PRN for a single bolt, and we have 6 bolts, it's pretty simple from there. So I'm actually going to write table 7.1. Okay, so we got a bolt shear capacity for this connection of about 481 kips. Okay, now that's for bolt shear. For bolt bearing, we have to do the bolt bearing computation twice. Okay, the first time we're doing it essentially based off of these values right here. We have a bolt spacing of 3 inches an edge distance of 2.5 inches, and a thickness of 3/4. So you go through, you calculate your clear distance for the edge bolts, your clear distance for the interior bolts, 2 times your bolt diameter, and you find that tear out's going to govern for each of those because each of these two values are less than 2 bolt diameters. So you say, all right, I can calculate the bearing capacity for an edge bolt and the bearing capacity for an interior bolt as follows. So 1.2 TFU times the minimum of either LC or 2 times your bolt diameter. Go through and chug all that out. Recognize that that connection has 2 edge bolts and it has 4 interior bolts. So chug it out and you'll get a nominal capacity of 610 kips, but phi RN, don't forget your phi value, your 0.75. So if you compare this value to the bolt shear capacity, the question is what's going to happen first? Are we going to fail the bolts first or are we going to fail the plate first? And the answer is the plate, because the plate capacity, the design capacity is 457 kips. Bolt shear was like 480. So we're going to fail the plate first. This is what governs the design. Now let's also be clear, this is just one case of bolt bearing. We also have to look at the cover plates as well. So basically, we're redoing that entire computation with these values right here. Now what changed? Well, the bolt spacing stayed the same, but we have a smaller edge distance and we have a larger thickness because we're just accounting for both of the plates at the same time. Instead of calculating the capacity of a single 1/2 inch plate and doubling it, I'm just going to double the thickness right now just so I don't forget. Okay? Now I think there was at least one person that went through and actually calculated the capacity. I think it was Mr. McCracken. What did you get for this? That sounds right. So phi RN 558, something like that. We'll just leave it at that. So, in other words, if you go through and carry all of those bolt bearing calculations again for those numbers, and I'm not going to repeat it because it is literally the same thing we just did, just different values for plugging and chugging, you'll get a capacity of 558 kips. So those cover plates are just fine. There's nothing wrong with those. In fact, it's probably worth discussing taking those cover plates and making them, instead of 1/2 inch thick, maybe make them 3/8 or maybe even a little thinner because they're certainly not governing the design. So all in all, that capacity is fine. So if you wanted to express what is the design capacity of this section as a whole, what is it? You tell me. There we go. So phi RN is 457.7 kips, and that's the answer. Now let's also be clear, there's still gross section yielding, net section fracture, and block shear. I'm just not doing that on this example because, I mean, I think we've beat a dead horse with all of that stuff. Sound good? All right. I'm going to erase this as well. This had really nothing to do with this, so I don't want to confuse things down the line when we start doing exam reviews and whatnot. What's that? I had nothing to do with this. All right. Sound good? Okay. All right. Does anybody have any questions about analysis of bolted connections? Because if you understand that, then design really is pretty simple. Everybody good? All right. So to design a bolted connection, I mean, it really is quite simple. Okay? All you do is you say, all right, I got 100 kips on this connection. Each bolt in shear could hold up 10 kips. So 100 into 10, I need 10 bolts. I swear it's that simple. Okay? It is that simple. So we determine the design load, the factored PU. We determine the shear capacity of one bolt. We divide to obtain the number of bolts. We do something very similar when we look at welded connections because we take the design load, then we determine the capacity of a single inch of weld, and then we divide to say, well, how many inches do we need? It's that simple. Okay? Now, that's not enough. I mean, just say, oh, you need 10 bolts. Okay. That's not enough. Okay, you have to actually lay out the connection according to prescribed requirements. So make sure that you've got bolt spacing met and you've got edge distance requirements met and what have you. Okay, so you lay out the connection, but let's also be clear that is not enough because let's take this connection. Let's say I did that. I factored the load. I divided the capacity of one bolt to say I needed what 5.89 bolts. I rounded up. I say okay, let's use 6 bolts. then I can space it out according to edge distance requirements, right? That's not enough because I still need to validate the bolt bearing capacity. Just because I've met bolt spacing and bolt edge distance requirements, that doesn't mean that the connection is automatically going to resist those loads. I have to go back and check that whole 1.2 LCTFU and all of that. So the final step is to check bolt bearing if needed. Okay, so you still need to go back and do all of that. Sound good? All right, it's really that simple. Okay, and if your connection doesn't work, you've got a number of options. Let's say you check bolt bearing and bolt bearing fails. Maybe, I don't know, increase your bolt spacing a little bit. By making your bolt spacing a little bit wider, that's going to up your bolt bearing capacity because, again, bolt bearing capacity is it's checking that plate against failure. And if the bolts are spaced farther apart, that's more room for the plate to develop that capacity. Sound good? All right. So let's design and lay out the bolted connection as shown. So we've got two plates that are, let's see, 12 inches wide and 7/8 inches in diameter. Okay, now we got 3/4 inch diameter Group B X bolts. Okay, we've got A572 50 plate, and we'll design for the following service loads. So I've got a dead load of 115 kips and a live load of 160 kips. The live load's already reduced, ain't got to worry about that. Those are service loads, which means step one, what do I need to do to those loads? Factor them. Okay, so let's go through that. All right. The funny thing is, I'm also going to kind of break out those times tables that you learned in what, 4th grade or 3rd grade or something like that. It's actually going to become somewhat relevant. All right. Example 9. Okay, so let's start off. Let's get a few properties. So A572 grade 50 steel. Okay, so we're going to need some material properties associated with that. Specifically, we're going to need the ultimate tensile stress. We're going to need F sub U. So what is F sub U for A572 grade 50 steel? What's that? 65 KSI. So F sub U is 65. Sound good? All right. Now help me out. So you just wanted to go ahead and write that out. Now you told me the first step was the factored load. So factored load. So we have here and here. I'm going to do this. I'm going to put table 2.4. Okay. So you told me the dead load was, what was it, 115? And what was the live load? Now what's going on back here? So tell me what to do. There we go. There we go. I want 60. Nope, come on. I'm getting ahead of myself. All right, so what do we got? 394. Do I got a second on that? All right. Everybody okay with this? All right. Okay, so let's look at connection design. Okay, so let's look at bolt shear capacity. All right. Now, does anybody remember how we're going to determine bolt shear capacity, where we're going to look in the manual? You have your manual. Uh-oh. You were like, I'm breaking it out. 7-1. There we go. Table 7-1. Everybody got that tabbed? See, so right here, available shear strength of bolts. Everybody remember that? So help me out. What information am I going to need to look up this quantity? Let's talk about the bolt diameter. What's the bolt diameter again? All right. What group am I in? BX. Or group. All right. Am I in single shear or am I in double shear? I got single shear. Does anybody else agree with that? Good. That is right, because it is single shear. Yep. What's that? No, what'd you say? Pretty thick. It has been referred to as the Steel Bible by many a student. What is PRN? You tell me. 27.8. Do I have a second on that? All right, sound good? Okay, all right. So help me out. To get the required number of bolts, all right, what do we got? We need the number of bolts is essentially, well, let's just keep it simple. We have a factored load of 394 kips. We got 27.8 kips per bolt. So you tell me what to do. Just divide them out. So I think what do we got? 14.17. Do I have a second on that? 14.17 bolts. There you go. no, that it'll hold. Yeah. You trust like Grandma being on that one? Like you said, she's tough. Now let me be clear. Let me be clear on something, okay? Let's say that number, instead of being 14.17, let's say it was 12.17. What would you do? No, hold on. Say that louder. 13. Okay, now let's also think a little practically. What's the problem with using 13 bolts? Say no. What were you said? Unlucky number. What did you say? Yeah, okay. There you go. You have a nice little grouping of bolts. But if you have, it's a prime number. I told you that those multiplication tables that you learned back in 4th grade, that they would matter. That's too much for college level engineer. We got to stop at 1st, 2nd grade. That's where it's got to. No, in all seriousness, think about what's going on. I mean, honestly, I don't even know that I would specify 14 bolts, because 14 bolts would have this big long row of 7 bolts, 7 times 2, right? It wouldn't collect that connection to a small grouped area. But 15, like you said, 3 times 5. It's a nice, small little region. Honestly, that's probably what I would do. Hey, now hold on. Say that again. There you go. That's actually, in a practical design scenario, that's probably a better answer, Just go with a different bolt, or go with threads included or threads excluded versus included, although we don't have that option here. but maybe using a bigger bolt and collapsing that down into a more manageable connection. Do you see what I mean? I mean, you got to design a connection that makes sense. Okay? Is everybody okay with that? This is an important discussion to have. Everybody all right with this? It's a prime number, right? You didn't think prime numbers would show up again, right? Why did no, no. No, whoa. No, hold on. Ask that again. Like, no. Well, all right, no, hold on. Let me ask that. So you're saying why not? Are you asking why not use 13 bolts? Okay. All right. Now hold on. Let me respond to that. Okay. Here's your member. Okay. Let's say here's your member that's being yanked on, right? Now here's a 13 bolt connection. Okay. So you're going to have a gusset plate that's like this long, and a gusset plate that's this long, you know, on each end. And you're literally going to have, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? That's what you're saying. Now, what I'm saying is this. I'm saying here's my design. Assuming it's the same member size. I'm saying we only have a gusset plate that's about like that. And we just collect those bolts in a smaller group. You get the idea of the scale? That's going to, no, I'm serious. Now imagine this member is repeated 80 different places in the structure. That is a lot of additional steel that's just being wasted, okay? You got to think larger terms, think of the whole structure. That's just going to make those connections ridiculous. You see what I mean?
Or if you're 13, why couldn't you use a stagger pattern like 4x4?
That's exactly, okay, that was going to be my next point, is that if you wanted to go with a staggered connection, you could do that as well. The only
if you want to keep it symmetrical.
Yeah, what I'm trying to do right now is just keep everything grid-like and simple and easy to understand. But going to what you're saying, you're exactly right. You could do 4, 5, and 4, and then there's your 13, and then you could just stagger it. But then you've got to make sure that you're meeting spacing patterns across the board. That's a good point as well. Is everybody okay with this? I want everybody to understand the larger potential options, but I'm saying if you're going with a grid-like pattern, don't pick something like 13 because it prime numbers.
Do they actually try and avoid stagger patterns if they can?
No, I'd actually say the answer to that's no, because nowadays you have CNC machines and things like that where I can just take an AutoCAD or a MicroStation file, plug it into the machine, and it will just drill the holes for me. So as long as it fits and it's easy to put together, that's a non-issue. And in many cases, staggered connections it can increase your net area and ultimately affect your design. I'm just saying from a calculation standpoint, that's not where I would start. I would start with a nice grid-like pattern. And if I did not have any other option to affect my design without substantially increasing the weight, then I'm going to try and start staggering out a connection. Does that make sense? I'd just keep it simple with a nice grid-like pattern. Sound good? Everybody else, this is good stuff. No, you can't. No, I heard you say that. You can't not ask after me hearing you say that. No.
Can you design one really big bolt?
No, hold on. Let me respond to that. There are connections out there that don't need a lot of bolts. Tell you what. No.
Guys up there with the wrench.
All right. No, hold on. You're looking at like thousands of kips of load. No, hold on. You're raising a really good point. I'm gonna look at the flip side. Go. Hold on. No, we're not gonna have concrete repeated. No. All right. Go to the awning that's between the old engineering building and the new engineering building and look up. Look at those floor beams that are framing in. And look at some of those connections that only have like 2 bolts, okay? There are plenty of instances where, honestly, the shear force on one of those beams due to that snow, it's not a lot, okay? It's really not a lot of force. And you really probably don't need any more than 1 bolt. You place 2 in there for OSHA requirements and for redundancy. I mean, for instance, there's an OSHA requirement that says, okay, if you're erecting a structure, all right, there's a requirement called the 2-bolt rule. In other words, you're erecting a structure, so you got a crane that's picking up some large piece of steel, right? And say it's a beam going into this building. So the crane's lifting it here, and then the crane holds it there, right? Crane's keeping it levitated there in place, okay? Then you got the iron workers installing bolts on either end. The crane won't let go until you got at least 2 bolts in on either side, okay? That's just basic, because what happens if it's installed improperly and one of those bolts snaps? Somebody on the ground's not having a good day, okay? You see what I mean?
Yeah, so use slightly smaller.
I don't think a hard hat's going to help if you got a W30 by 90 that's just 30 foot long. At that point, you need like Magneto or somebody there to help.
Hey, throw me that 2-foot socket.
All right. Now, in all seriousness, did that help answer your
It wasn't even my question.
Now that he asked it, he's clear. All right. Getting back to steel. Now, hold on. Getting back to steel designs. Anybody have any questions? I mean, this is good stuff, all right? You are making a good point that you could calculate, not on the large end, I'm saying on the small end. You could calculate the force on a connection and get that you only need 1 bolt, and that's possible. But just from safety considerations, I mean, I'm not going to do any less than 2. I'm not doing that. Anybody else? All right. Now, so you said 3 times 5, right? Well, that's exactly what we're going to do. All right. Now, in order to lay out that connection, we need to discuss some layout parameters. So connection layout. Connection layout. So we need 2 things. We need a bolt spacing, and we need an edge distance. So help me out. What is our preferred bolt spacing for a given connection? No, well, there's 3 inches, but there's also something that code specifies. What's the code specify? All right, hold on. Let's go back to this. How do you calculate min and max bolt spacing? Now, I think you're on to something right there. Go right there.
2 2/3 bolt diameter.
Okay, so that is the minimum bolt spacing. What's the preferred bolt spacing? 3 times the bolt diameter. So let me go. Remember these? Bolt spacing requirements and edge distance requirements. Minimum bolt spacing is 2 2/3 times the bolt diameter, but a preferred bolt spacing is 3 times the bolt diameter. 3 inches is very common, but if I'm trying to save money, I'm going to go with what the code tells me to. And the code tells me 3 dB is preferred, so that's what I'm going to use. So 3 times the bolt diameter is what? So let's see. S preferred, 3 dB, 3 times, what's the bolt diameter? 3/4. And that's what? 9/4, so 2.25. Now, what is our edge distance? So let's keep this simple. Let's go back to basics. If I'm specifying an edge distance, I don't have a preferred. I have a minimum and maximum. So if I'm in design mode and I'm trying to save money, do I want to design based off of a minimum edge distance or a maximum edge distance? Minimum, right? Minimum edge distance is going to mean less connection material required for that connection, ultimately less hit on the wallet of my client. So what is the minimum edge distance for this connection going to be? No, that's the maximum. Gotta look it up. open the manual. No, we're going to find this one together. 16.1-1, what is it? No, the page. 123, 16.1-123. And you said that the minimum edge distance for a 3/4 inch diameter bolt is 1 inch. So that is page 16.1-123, table J3.4. Does everybody see that? Not too bad, right? Any questions? So here's how I'm going to lay out this connection. All right? Does everybody have all this? Everybody got this? I'm going to move on. Example 9, right? All right. So remind me, how wide is this plate? No, wide. 12 inches, right? So this is what I'm going to do. And I've got a lot drawn over here, and I'm probably going to erase. You said 3 by 5, so I'm going to do 3 by 5. 1, 2, 3. 1, 2, 3. 1. There we go. If this dimension right here, bless you, is, if that's 12 inches, what's each of these? Three inches. Okay. Now, what else? What's this distance going to be? This one on the bottom. What is that? 1 inch. That's the edge distance. And then, what are each of these? 2.25. Oh. There's my design. Now let's be clear. This is a trial connection layout for a number of reasons. All right? Somebody spit out a limit state that we're going to have to check for this connection. Something. Okay, that's not a limit state. No, say bolt bearing. Okay, that's one. Now, ultimately, what are some others that we'd have to check? Block shear, net section fracture, gross section yielding. One more also. Associated with tension members. Wasn't a limit state. Slenderness. We're going to have to check slenderness. So let's just sort of list all that out. All right, so remaining tasks, if you will. For threaded rods. And again, it technically is not a requirement, but we ought to check it. Remaining tasks. So 1, bolt bearing. Now help me out. When we do bolt bearing, we know our bolt spacing, it's what? Our S distance is what? No. 2.25. Remember, spacing along the direction of the loading, right? So this is what I'm going to do. For bolt bearing, I'm going to say S is 2.25. I'm going to say the edge distance is what? 1 inch, right? All right. What's the thickness? 7/8. What is FU? All right. Here, I'll sort of bracket all this. So our bolt diameter is 3/4. So you need that to calculate the hole diameter, which to calculate the hole diameter, we take the bolt diameter and we add what? There we go, 1/16 of an inch. Now, the final point I'm going to make is this. How many edge bolts do we have and how many interior bolts do we have? 3 and 12. All right, so edge bolts is 3. Interior bolts is 12. So based on that data, you should be able to calculate bolt bearing right now. I mean, literally calculate your hole diameter, calculate LCE and LCI, calculate 2 times your bolt diameter, then 1.2 TFU times the minimum of LC, or your 2 times your bolt diameter for your edge bolts. Do that again for your interior bolts. 3 times your edge bolts, 12 times your interior bolts will get you your nominal capacity, and then adjust by phi. I know that's convoluted, but we literally just did that last time. Yes?
Remind me when we use and why we use 1/16 for the bolt diameter.
Okay. All right. So when you are checking bolt bearing, which is what we're doing, we're not asking ourselves how much of that little bit of material around the bolt will contribute to the rest of the member. We are literally just looking at the physical dimensions of that plate right there at the bolt. When we added 1/8 of an inch, we did that because we were adding a 1/16 for 2 reasons. 1/16 was added because we are physically drilling the hole a little bit larger. Another 1/16 of an inch was added because that little bit of material right around where the hole was drilled, we said, well, that's not really efficient in transferring load to the rest of the member. So when we were looking at tension members, we didn't care about that. But we're not looking at this as if it's a big tension member. We're looking at it as if it's, we're looking at the physical capacity of the connection. My point is, for bolt bearing, we're looking at the physical dimensions in the hole. When we look at gross section yielding, net section fracture, and all that, we're asking what's the strength of the member as a whole. That kind of answer your question?
Bolt bearing. That's when you do 1/16.
Yes. But I want you to understand why. Does that make sense?
Kind of, but I'm not going to say fully.
Well, again, when we calculate, let's be clear, when we calculate the bolt bearing capacity of this connection, we're not looking at this thing as one big member. We're literally asking, what is the bolt bearing capacity of this hole? And then what's the bolt bearing capacity of this hole? And what's the bolt bearing capacity of this hole? And just adding it up. When we were looking at tension members, we were saying, no, let's look at the entire member as one cohesive element. Do you see what I'm saying? And I'm saying that if you actually drill a hole, so here's your bolt right here. First off, when you drill a hole, you drill the hole a little larger, okay? But for tension members, we also said, well, this little bit of material right here around where we drilled that's got a bunch of burrs and maybe some damage due to sub-punching and whatnot like that, we just said, you know what, we're not going to consider that effective for the whole member, okay? Does that kind of make sense? Is that better? Is that a better answer? Yes. If I go out with a caliper and measure it, it will be a 1/16 of an inch larger. That is the facts. Okay? Yes, sir. That's a good question, but we don't do that. I mean, that's why, we don't do that in steel structures more often than not. That's why we have bolts and nuts and washers. We don't usually do that. But you got to understand, we're not talking about an engine or something like that, where that's a little more common. That fair point? Or fair answer, I guess I should say. You have threaded rods, but then you would just attach a nut to it. Everybody okay with that? More often than not, we don't do that. I'm sure there's some industrial structures here and there where they do that, but we don't more often than not. Okay? All right. Couple other things. So we have bolt bearing. We also mentioned gross section yielding. We have net section fracture. We have block shear. And I would say that the most likely block shear failure path is probably going to look something like this. That's probably the most common one, because just looking at the dimensions, like if I had another shear path that's going like this, again, your block shear paths have to surround all of the bolts in the connection, but when I'm defining block shear paths, I'm trying to define the path with the smallest amount of area, because that's more than likely how it's going to rip. Does that sound good? So you could have a path that goes, down, over, and down, but that's increasing. That's another 10 inches of area in shear, and you're losing, only 3 inches in tension. It's more likely it's going to fail that way than with all that additional shear path. Does that make sense? Everybody okay with that? All right, and the last one, which it's not a limit state, but we also need to check this. Of course, we can't check slenderness for this problem because we don't know how long the member is. This member could be 5 feet long or it could be 50 feet long. But let's also go back to some mechanics of deformable bodies. You don't have R, right? You don't have the radius of gyration. Anybody remember how to compute R? Been a while, right?
Yeah, that's what this stands for, right?
You're kind of right, and it's in the manual too. So you calculate first off, that shape is a rectangle, right? So can you compute the area of that rectangle? 12 times 7/8, right? Then you got the moment of inertia, BH cubed over 12. So you got the moment of inertia and the area, I over A. Take the square root of I over A, you get the radius. Okay, all right, we got some folks that remember that. But okay, sometimes it's called K, we call it R. Yeah, you're talking about the same thing. So we don't call that in here because we have another term, K, and we didn't want to confuse them down the line. So, everybody okay with this? No, it's called R. I mean, we've been looking up Rx and Ry. We have Ks that we're going to look up later. Those are effective length factors for columns, but we'll get to that down the line. Anybody got any questions? Okay, so here's what's going to happen next. So I know that I can imagine that some of you are like, okay, I'm going to forget this until he assigns a homework. Luckily, this isn't that bad. This was a pretty basic example. So we said, all right, now that we've got this, when we come back from the exam, we're going to talk about, I've got some additional questions which aren't that big of a deal, but we're going to talk about slip critical connections when we get back. One other point I guess I'll mention just for the heck of it. So if you have a splice connection like this, okay, so this is what a splice connection looks like. So I've got let's say member A over here and member B over here. So they're both 7 by 1 inch main plates. And I'm yanking on them. And I've got a piece here and a piece here, so I want to splice them together. So I put a series of splice plates on the end to sort of say, okay, here's member A, here's member B, and I want to connect them together. I got a member up front, or a splice plate up front, a splice plate behind. Does that make sense? Everybody okay with that? Now, the question is, when I start analyzing that connection and designing that splice, I need to know, let's just take bolt shear, okay? All right, so I can determine the capacity of a single bolt and then multiply by the number of bolts. The question is, if I'm doing a splice connection, how many bolts do I consider? It's a trick question, kind of. You tell me, looking at this connection, how many bolts would you consider? So somebody said 8, but what did you say? 4. The answer is 4. The reason why is because half of these bolts are working to transmit load to the member on the right. The other half are working to transmit load to the member on the left. Okay? Think about it like this. Samurai sword or lightsaber right through the connection. You know what I mean? These bolts are experiencing load to transmit the load this way. The other ones over here are working in the opposite direction. So when I do a splice connection, something like this, I don't look at the entire connection. I cut it in half and I size this plate, or the center plate and these cover plates for that load transmitting to the one side. Yes, sir?
So do the cover plates see 2T?
No, they see half a T. Yeah, because that's just basic, like, statics. Because if I cut a section, think I got T going, I got to have T going this way. So each one carries up half that. Does that make sense? You mean here? Not really. Just keep it simple. I mean, what's going to happen is this. So let's keep it simple. So your bolts are going to be spaced at 3 inches. You're going to size these based off of minimum edge distances. So think, like, going back to our last example, like this bolt spacing was 2.5, but the edge distances were 1 inch. So there'd be 1 inch here, 1 inch here. So you'd have a little bit of a gap. 2 1/4. Wow. That was we'll go with like 2.1 or something. That wasn't even that big of a mistake. I'm talking, no, that's a good point. That's a good point. I'm talking about gaps right here, like between the plates where water can get in, but it has a tough time getting out. I'm talking about, essentially I'm talking about capillary action. If you remember that from chemistry or fluids or whenever you talked about that, that's what I'm talking about. When the water gets in, but it's got a tough time getting out. Water can easily get out of here. And when it gets windy and dries up, it's going to go away. I'm talking about the water that gets stuck. That's a good point. Everybody good? Come prepared to ask questions on Wednesday. We celebrate on Friday. That's all I got.